YouTube traffic, this is 345 Delta Foxtrot, ready to record another YouTube video. YouTube traffic. This is my disclaimer, same as last time. If you haven't already seen it, please take a few seconds to take a look at it. Okay, today's topic is aluminum alloys, and this is going to be a two-part video. We'll cover about half of it in this part one. If you're building a Vans RV, any Vans RV, not just an RV10, you're going to be building an aluminum airframe. And in the instructions, if you go to chapter 5, which is titled General Information, the very first sentence in chapter 5 is, the aluminum skins used on RV aircraft are all 2024-T3 alloy. So what is this 2024-T3 stuff? That's what this video is going to be about. Okay, the first thing we need to talk about is how do you spell it and how do you pronounce it? Is it aluminum or aluminium? In 1925, the American Chemical Society adopted aluminum. In 1990, the International Union of Pure and Applied Chemistry adopted aluminium. Today it's mixed. English speakers in North America use aluminum and everybody else in the world uses aluminium. Since I'm an English speaker in North America, I'm going to use aluminum. However, I believe that in modern technical publications, the standard is to use the aluminium spelling. Okay, it turns out aluminum is the third most common element in the Earth's crust after oxygen and silicon. It surprised me that there's actually more aluminum in the Earth's crust than iron. So you could probably start mining aluminum in the dirt in your backyard. However, it wouldn't be economical. If you want to try and mine aluminum economically, you want to go to a richer source. And typically, what is mined is bauxite. Bauxite is a sedimentary rock, and it's composed of various minerals, as all rocks are. In the case of bauxite, it's composed of aluminum hydroxide minerals and some mixtures of silica, iron oxide, and some other stuff. Okay, there's a zillion different aluminum alloys. So somebody went to the trouble of trying to organize them. The Aluminum Society of America or somebody. So this is what they came up with. The type 1 alloys are basically pure aluminum. They're greater than 99% aluminum. The type 2 alloys, the primary impurity is copper. The type 3 alloys, the primary impurity is manganese. Type 4, it's silicon. Type 5 is magnesium. Type 6 is magnesium and silicon. Type 7 is zinc. And type 8 is everything else. So of course 2024 is type 2 and the primary impurity is going to be copper. So here's a table of the compositions of some different alloys, not just aluminum. There's aluminum, steel, and brass in this table. The first column is 1100 aluminum. So that's type 1, and it's basically pure aluminum, greater than 99% aluminum. The second column is the 2024 aluminum, and as you can see, it's about 93% or so aluminum, about a little over 4% copper, 1.5% magnesium, and about 0.6% manganese. Medium carbon steel. Carbon is a big alloy element for steel. It affects the properties a lot, and a little bit goes a long way. 0.42% is considered a medium carbon. About 0.8% is about as high as it goes. So anything in the 0.8 range would be high carbon steel. It has some cobalt in it, and the rest is iron. And you might notice that in this column, the numbers don't add up to 100%. And that's because this is the average of a bunch of different medium carbon steel alloys. We're not talking about just one particular alloy. The next column is stainless steel, and what makes it stainless is the addition of chromium and nickel. About 18% chromium and about 11% nickel. There's also a little cobalt in there as well, and even a little bit of aluminum. Now, brass is an alloy of copper and zinc, and it also has a few percent of magnesium in it. Okay, let's look at the mechanical properties of these alloys. The first one is density. I think everybody knows what that is. In this particular case, it's given in metric units, grams per cubic centimeter. But the rest of these you might not be all that familiar with. Brinell hardness is basically the size of a dent. You take a very hard spherical ball. I think the diameter is typically about 1 centimeter, and you push on your alloy with some given force, and then you measure the size of the dent. So it's basically a fairly straightforward measure of the hardness. The tensile strength ultimate is you take a bar or a rod of your alloy and you pull on it until it breaks, and you record the amount of force it took for it to break. Now, tensile strength yield is similar, except you take your rod and you pull on it until there's a permanent change, and then you record how much force it took for that to occur. The shear modulus is a measure of the stiffness. The modulus of elasticity is a measure of rigidity or stiffness. The shear strength is the force required to basically punch a hole in the alloy. Fatigue strength, there's different ways to measure fatigue strength. You can basically think of it as how much can you bend it back and forth before it breaks. However, a totally different way of measuring fatigue strength is you start off with a small crack or cut in your alloy, and then you pull on it and you measure how fast the crack or cut propagates. And there's other methods as well. Okay, on the previous table, steel won in every category. Let's go back a second. You can see steel in the darker blue. It is harder, has a higher tensile strength, etc., than aluminum by far. However, in an aircraft, you want both high strength and low weight. So what we really want to do is look at the strength to density ratio. So if you just take the numbers in the previous table and you divide them by density, for example, in the first row, we have the Brinell hardness divided by the density. This is what you get. And now you see that the 2024 aluminum is winning in every category. So what is this copper in the 2024 alloy doing for us? How much stronger is 2024 than 1100 alloy? So you just take the numbers for those two alloys and you take 2024 divided by the 1100, and that's this last column here. And you see that the 2024 is about 2x stronger than the pure aluminum, which is a pretty big deal. Okay, what is the dash O and the dash T3 that I've mentioned or you've seen in the previous slides? That's the heat treatment or the temper of that alloy. And the dash O means that it's just been annealed, and it's been annealed at a little over 400 degrees C for a couple of hours, and then it's slowly cooled. So basically, you like pour it into a mold and you let it cool, something like that. The T3 alloy has a significantly different heat treatment. It's solution heat treated, and it sounds like it's heat treated in a liquid, a solution, but that's not the case at all. It's heat treated in a furnace in air. And what happens is you heat it up to about 485 degrees C, and that's hot enough to dissolve all of the impurity elements that you've added. The copper, the magnesium, and the manganese all dissolve in the aluminum, and they intersperse themselves fairly uniformly in the aluminum. And then it's rapidly cooled. It comes out of the furnace, and within seconds, it's cooled. In this case, I believe it is cooled in a liquid. They probably just dip it in water and cool it very rapidly. Then it's cold worked. That's step 2. You roll it out to whatever thickness you want or need. And then step 3 is an aging step. And for 2024, I believe that it's just aged at room temperature. So all you have to do is let it sit around for a couple of days. For other alloys, you probably heat it up 100 or 200 degrees C, and so that you can age it a little more rapidly. So how much does this heat treatment help? Well, you did the same thing. You just take the numbers in the previous table, and you take the 2024 T3 divided by the 2024-O, and that's the third column here. And you see that you get another factor of 2 to 3. So that's probably an even bigger deal than adding the copper in the first place. Okay, so what is going on here? Why is this heat treatment affecting the mechanical properties of the aluminum? And there's multiple effects going on here. I'm going to talk about 2 of them. I believe that they're probably the 2 biggest effects, but I'm not an expert in the field, and if you have a slightly different or better explanation, please post a comment. So the first thing is the grain size is significantly different. The dash O material is cooled slowly, so it has a much larger grain size. This is typical for growing of any crystals. For example, that's why Granite has a much bigger crystals than rhyolite. The granite cools very slowly under the earth, and the rhyolite cools on the surface of the earth, and it cools much more quickly, so it has virtually no visible crystals. So the T3 is cooled very rapidly. As I already mentioned, it's quenched in water or something like that. And it has a much, much smaller grain size than the -O material. So turns out that's good. And the question is, why is that good? So say you bend the aluminum and it starts to slip. You start to form a slip line or a slip dislocation. And there are preferred weaker planes in an aluminum crystal. I think typically the 100 plane is a weaker plane. So say you have a slip line propagating in some direction in one of the aluminum grains, say it's propagating this way. And it comes to a grain boundary, and say the next grain, instead of being oriented in this direction, it's oriented off at some angle, this direction, or this direction, or this direction. So the slip and dislocation either has to just plow through a non-preferred orientation of this next grain, or it has to try and go around it or something. And so it turns out that the hardness and the mechanical properties of the alloy are basically dependent on how many grain boundaries the slip and dislocation has to cross. So the smaller the grain boundaries, or the smaller the grains are, the more grain boundaries it has to cross, and the harder the material is. Okay, the other effect is the effect of the copper aluminide precipitates. Copper aluminide is CuAl2, and I've already mentioned that the copper is the primary impurity in the 2024 aluminum. So if you cool it down slowly, the aluminum atoms like to be with other aluminum atoms, and the copper atoms like to be with other copper atoms. So you end up with these grains or crystals of fairly pure aluminum, and in between, in the grain boundaries, you end up with blobs of copper. And that's not really what you want. So in the T3, what happens is you heat it up a little hotter, up around 485. The copper dissolves in the aluminum, and it gets dispersed fairly uniformly. And then it's cooled very rapidly, and the copper does not have time to move. It basically stays where it's at, uniformly dispersed in the aluminum grains. And then you do the aging step. And in the aging step, the copper can move around a little bit, and it joins up with some nearby copper atoms and forms a small particulate of aluminum, copper aluminide, CuAl2. And it turns out that there's an optimum size and density of these CuAl2 precipitates. If they're too small, a slip line or dislocation comes along and it just goes right through them, like they're not there. So, however, if you only have a given amount of copper, and so if they get bigger, there's fewer of them. So if they get bigger when the slip line comes up to 1, then the big aluminide precipitate can block it from propagating. But there are much fewer of these larger precipitates. So there's a good chance that the slip dislocation will not hit any of them, we'll just miss them. Or if it comes close to 1, it'll just go around it. So like I said, there's an optimum number and size of these copper aluminide precipitates. And so you just adjust your aging step in step 3 here. You just adjust the time and temperature to hit that optimum size and density of aluminum copper precipitates. Okay, that's it for part 1. We're about half done talking about aluminum alloys. Please watch part 2 before you leave any comments. Hopefully, I'll answer some of your questions or all of your questions in part 2. So that's it. Thanks for watching, and please watch part 2.